So you can set this up to be equal to the initial conditions. And I did put my y2 prime. I was a little worried I'm not going to have the y2 prime there. But you see, like, you can set up your initial conditions into this form. And then you can take that thing and set it up just the way you do it in linear algebra class. The right-hand side is your B vector. I think even Strang uses that notation. And then you have the matrix of coefficients, and you can solve this equation. My favorite book for that class is David Lay's book. That's so, like, it just has the blue boxes, the main points are there, and it builds up so that you get kind of, even if you don't get it at that time, like I didn't get it because I was not a serious student. You're better than me. But if you go back in time, you can go, oh, I see that, like, blue box thing. I remember what this was. If you look in the Lay book, he has like this buildup, but I forgot what I think he calls it, the invertibility theorem or something like that. And he keeps, he just keeps adding to it. At one point, he adds in the easiest way to tell if a 2x2 matrix is invertible. So the whole point is you can't solve this unless A is invertible. So do you remember what that was from linear algebra? I don't know if you guys have got there yet. How do you tell if a matrix is invertible?
It's diagonalizable.
Now, you're already there? Diagonal? Okay. Does anybody remember?
I don't think we've done that so far. Right now we're doing transformations.
Okay. How do you tell easily if you have independent columns, like with like a one blow? Those things are really hard. Gaussian's awful. It's hard. Easy.
Be like a factor of another.
Like if it's the basis.
Remember taking determinants?
The basis of the column space. Oh yeah, I mean determinant is not even.
That's the easiest way, right? I'm kind of a weasel, so I look for like easiest path. Easiest way to tell if A is invertible is that the determinant's not zero.
What they have us do now is find the two coefficients, C1 and C2, and if they are zero, then they're linearly independent.
Okay, you're going to get to a point where you have the determinant. It's easy to calculate. You did it in 255 or 205, but my son tells me he doesn't remember anything from 255, so you probably don't remember it. But from linear algebra, the solution exists if the determinant is not zero, and the determinant is super easy to calculate. It's for a 2x2, this is the formula. Right. And so you can just put that in there, and you want that to not be zero. When we actually compute things, we want the easiest thing possible. Now, determinants for a 3x3 are terrible. So the Wronskian is actually only good for 2x2s. If you want to program it.
They have us do 3x3.
Yeah, you have to do that. They probably did the pivot factors and then that's not. If you had an n by n, like 100 by 100, like for real applications, you have lots and lots of equations. And so nobody gives like a cookbook problem from a textbook and says, find the determinant of this 3x3. They have like a real problem has hundreds and hundreds of things in it. Like the microbiome stuff we get, that's huge. And it's sparse. But I'm not gonna calculate determinants on the computer with that. That's gonna be horrible. I already broke one computer. I don't want to break another one. So when they tell you use Google Colab, use Google Colab. I didn't listen. And it ate up my government-issued computer. So this determinant is called the Wronskian determinant. I've heard the Wronskian actually being called the matrix and the determinant referred to this determinant. Your book actually calls the Wronskian the determinant. So I'm trying to be consistent and call it Wronskian determinant so that you know that it's the determinant. It's sometimes just called the Wronskian.
I believe in 153 it was called the Wronskian.
The determinant, yeah, because they're using this book and they're lining it up to Stewart, so they're keeping the language the same. Once you have the determinant, they have this equation that in, I think it's called Cramer's rule, where you can solve matrix equations using the determinant, but it's super easy for 2x2s. You can either use that by hand or stick it on Mathematica and tell it to do it for you. And you get this C1 and C2 as symbolic solutions. So I'm going to depress you and say no one's ever going to ask you to solve a 2 by 2 thing like this, but you know, we all learn it so that we have that behind the scenes.
Are we dividing by the determinant there?
Yeah, determinant. It's just a number.
Right,
So
so-
since it's not 0.
Right, so we'll just do every term by.
Yep.
Right, right.
Not every term. This is a determinant on top too.
Oh, okay.
Like, so if you remember, you haven't got to Cramer's rule, but there's something called Cramer's rule. I think he actually didn't come up with that rule. I think he actually came up with the Maclaurin series. I don't know what these people did, but they swapped up the names.